welcome to After Hours Engineering, Episode 20. Now that we have range of RISC successfully synthesized, we can add CSRs back in order to reintroduce interrupts into the system. In addition, we need to use a phase lock loop, or a PLL, so that we can run the core at its maximum frequency of 18 MHz. It's about what the NPR routing tool calculates that it can do. So, let's go. We begin with solving our clock frequency issue first. The routing tool is determining that 18 to 19 MHz is the highest clock our software can run at. Yet we have that 25 MHz core clock. So we need to solve that first. And the way we're going to do that is using a PLL, or a phase lock loop. That's right here. The first place I highly recommend is you go to Folknology's MyStorm GitHub repo. And under their BlackiceEdge, they have an entire section that talks about and covers PLLs in all kinds of levels. I highly recommend that you visit this site and go through all of their documentation. It tells you how they derive the clock frequencies, how to run the open source PLL tool, everything. I highly recommend it. And then on top of that, to get to the actual documents themselves, I recommend that you look at the two spec docs that's out there. This one is on the PLL primitives, and it talks about how to set up the PLL core, which is what the tool will generate. And we'll take a look at that in a minute. That's what the PLL tool core is going to do right here. So we should see that come out as a Verilog source module, and we'll fill it out, or the tool will fill it out for us. The other document that I recommend you look at is the ICE system clock document, the PLL design user guide. And it'll cover a lot of things with the Folknology website, but it'll give you much higher detail level. It's specific to the actual device itself. So I highly recommend that. Now, once you've been through all of that and you read through the documentation, you'll get a better idea of how to use PLLs. So what are they in terms of software-wise, or in high HDL code? For that, we'll take a look at the generator code. Now, from a terminal, what you would do is you would run the ICE PLL tool. This will come with your MyStorm. Once you've installed MyStorm, you'll actually get a bunch of tools, and one of them is the ICE PLL tool. And you can give it a bunch of commands, for instance, the input frequency right here, and the output frequency, which I've set at 18 megahertz. Now, the reason why I set that to 18 is because the routing tool has determined that that's the fastest it can route the hardware on the circuitry in order to produce a fully functional CPU. If you just type this command directly, you'll get this output right here. Now, this isn't HDL source. This is just information that says, hey, you told me 25 megahertz with an output requested, and these are the parameters. If we go back to the document and take a look at these settings right here, you'll see that they're all right in here. They're all telling us what these values should be set at, and they're in both these documents here. So if I close this one down, you'll also see these listed in here. So once you have those, you can either manually set up one of the Silicon Blues primitives that they have, or we'll have the tool do that for us. In order for that to happen, we give it a few extra commands here, parameters, and it will generate a system Verilog, or actually a Verilog file for us. And I made a few tweaks over here to the left on that very file itself. And here it is. It's in our project for our range of RISC, and it's this PLL-SV file. Once I ran this command right here, out popped this code. Now, again, I changed it to system Verilog, but it's 99.999% identical to this. And here is that primitive that we've been seeing in the documentations. So we'll come back to the document and we'll look at the primitives that we can use with our open source toolchain. And the PLL40 core is one of the primitives from Lattice, which used to be Lattice purchased Silicon Blue. And in there, again, you can see all of the parameters that you can fill out and everything, but the tool is going to do this for us. It'll actually generate proper Verilog code that will use this primitive right here. So if we go back to the document, or to our source code, you can see right here is that primitive, and it's built it properly for us, giving it information like the divider R, div F, div Q, filter range, everything. It'll even give us a signal back, which we'll use to tell us that it's locked on to the phase, because phase lock loops are things that can drift, and you need to keep them locked on once you reach your target frequency. And that's what this is going to do for us. So we take this and verbatim, and then we'll go back to the top module and look for that PLL code. And there it is. I've included it in our make file. So I come up here to the make file, and I've added it into our code, and then I've instantiated it right here, giving it our core clock coming in from the board itself. The module outputs an estimate 18 megahertz clock for us. And then it gives us a lock signal that we'll use in order to move forward. We'll come into the reset, and we won't leave the reset until the PLL has locked on to the frequency that we want. It's pretty fast, and I highly recommend that you actually use the lock signal coming from the module, because your code may try to run before the signal has been locked, which can cause some really strange behavior from time to time. And so that's it. We've literally just used the ICE tool over here to generate a primitive specific to the Lattice ICE40 chip. And this is where we've deviated from the pure path of just pure HDL, where you could compile Ranger on pretty much any FPGA. At this point, we're now dedicated and locked on to the Lattice ICE40 chip. And so at this point, you probably would add macros in here to choose your target and use a different primitive in order to feed your clock. So this is PLLs in a nutshell. It's a huge high-level view of it. It's considerably more complex and challenging to deal with, especially when you need to deal with routing clocks into and out of the FPGA. The specs for the ICE40 actually have another primitive for pads themselves, so you can physically send your signals into or out of, either supply a signal directly to the PLL or route some of those signals out of the FPGA via the pads. But I'm not covering any of those. We're looking strictly at just the ICE40 PLL core. In the previous episode, I had removed CSRs to remove some noise from the code such that we could focus on the ISA. We're now going to add them back in. But before I did, I went back and re-evaluated the CSR instructions here by rereading the spec and finding out if there was some ways that I could simplify the design. The specs don't dictate precisely what you must do in your hardware. They just say that as a black box, this is what must be reflected with the instruction sets themselves. So I went ahead and simplified the design just a little bit. The code's almost identical, but I reduced the code to just manipulating the global enablement and the M mode enablement only by the instructions themselves, and the pending bit is controlled by the hardware. Now we look at the HDL code that supports the interrupt circuitry. It all starts with the top module as usual. The interrupt comes in off of one of the P mods here. It's being driven by a Pico RP2040. We scroll down and we can see that it is routed into the processor itself, which then will be routed into the control matrix that we have over here on the left. Now this circuitry is roughly the same as before. We look for a change in the interrupt or a change in a signal from the processor itself or from the control matrix. If it's coming in without that signal here, then we know the RP40 is triggering an interrupt, and so we set this flag. This flag will then signal the control matrix. So if we come up here, we can see that we're in the section of the control matrix clocking section. So on the next clock, so once the trigger is set, it's not actually going to set the pending bit until the next clock. And this will set it every single clock as it's coming in. Now I put a note here that originally I had this restriction right here that we wouldn't set the pending bit if we were already in progress for an interrupt. Now, weirdly enough, that really caused the routing tool to drop our frequency really low. But it turns out we don't need this condition right here. So I've left it off, which gave us the ability to run actually above 18 megahertz, but I'm still restricting it to 18. So for every clock, if the trigger is active, the pin has gone high, then we keep setting the pending bit. But that's okay, we're going to clear it shortly enough. So once that happens, if we come up here to the normal section of the code right here, in our original diagram, our original code is that on every prefetch, we check to see, one, the global is enabled, the M mode is enabled, and this pending bit is enabled. Now these two signals right here, as mentioned before, are only controlled by the CSR instructions themselves, but this one is controlled by the signal coming in off of the PMOD port. If we are in pending, which that signal would have gone high, and we're not in an interrupt, we immediately transition to IRQ0. We don't do anything as we were doing before. We were doing some crazy stuff with our status register, and it turns out we really don't need to do anything with that. We can use the instructions to control that. So it goes down to IRQ0 and moves the PC into this is our return address from wherever the interrupt occurred, and we jump then to the actual trap handler itself, which is specified in the MTVEC register. And I've set up some other signals down here in our clocking state such that we are again in the prefetch down here, and if we are pending but we are not in an interrupt cycle, we go ahead and set this signal right here. And it won't be cleared until we've done the MTRET or the MRET clear instruction itself. Also in IRQ0, we need to send a signal back to the other domain to say to clear out this trigger signal so that we're not constantly setting this pending flag all the time. It gets set. Now this particular design indicates or means that we can actually set the pending flag continuously, but it won't be honored until we've officially finished the current instruction, and that includes the trap handler, whereas before that didn't include the trap handler, which was this section of code right here. And we actually want that. There's the downside to that means that if your interrupt signal is coming in so fast and frequently that your actual code starves and only thing that runs is the interrupt routine itself. That's generally not a good design, but it works for us in this case. I can actually add this back in and restrict it. But if I do add this in, we'll actually lose interrupt requests as they're coming in. So this one allows us to, in the future, add in a queue such that every time a triggered IRQ comes in, we actually queue it up and allow to process any of them. But this is a super simple design, and I only wanted to get it started. So that's it. Now we come up to the final phase of it. So the trap handler is run. It does its thing. And when that's the case, the last thing the trap handler does is execute the MRET instruction. And what that just does is it moves the place where we interrupted back into the PC, and then we pick up where we left off. And this code will work, and we'll see it running on the actual hardware itself. In order to test the interrupt code, I've created two assembler programs, one for testing at 48 Hz, which you see over here to the left, and the other one for testing at 18 megahertz. They're nearly identical, it's just one has been adjusted to handle it. So real quickly, we'll just go through it at a high level. We do our usual boot, which enables and disables things. We eventually come up here, set up our registers for counting, and then we come down here and we enter in the domain loop. While it's looping around here, we may trigger an interrupt at any time, and when that happens, we add 1 to X5, hit the MRET instruction, and come back up to whatever instruction we interrupted on. It could be any one of these instructions right here. This E break will never be hit. This code will permanently sit there and count. Now this is designed to run at 48 Hertz. The one on the right is almost identical, but we've added in a few other things. For one thing, we added in this small section of code which adds a delay. Without this delay code right here, the 7-segment display would count so fast we wouldn't see anything. So by adding in this small delay, which is basically counting the X register right here, And if it exceeds X9, and X9 was loaded in with our delay count, so if we come down here, this is the delay. We'll count to FFF, and when we exceeded that number, we reset it back to 0, and then we increment the main counter itself, X3. And both of these will be routed. So I've done a little bit of redesign, and I'll show you that in the top module in a second. But the X5 is written out to the blade so that we can see the interrupts increment each time. So the blade's going to show us that every time I hit the interrupt, it'll increment it. And the X3 is routed to the 7th segment so that we can see that the CPU is constantly running and counting and doing things. And they both do the exact same thing. They both write to the blade and the 7th segment display. Now we will go ahead and compile the interrupt counter for the 48 megahertz. There we go, it's compiled. And now we need to build or bake that into our image. So we'll come over here and type make, and we'll let that run while it's building it. And we'll keep an eye on the little tiny blue LED there. It'll go out because that blue LED I've wired up to represent the interrupt signal that we have coming in. So let's go ahead and take a look at the code. And if we come over to the top module, right over here, and we look at our outputs, I've wired up the blade to have only the 4 bottom bits of the parallel port displayed. And that's going to show our interrupt counter. And I've set up the interrupt counter to only count to 8, and then it'll wrap around. If we come over here, the last 2 is going to be our interrupt in progress and our pending bit. And at 48 Hertz, we'll actually see those toggle briefly as it goes through its different types of states. So let's check up on our output here on the code, the terminal, bring that back up, and it's compiling. We'll look at the output, and as soon as it's done, there it goes. The blue light has gone out, and we're now loaded. So we need to hook up or attach, if you will, our 2 UART controls. The first UART that I have, let me bring up the terminal here, is the RP40, the Pico. And it's on USB 0, so I'll start that up, and I'll hit the letter H, and it shows me that pin 15 is high, and that's this pin right down here on the PMOD over to the left, just left of the Pico itself. And then I'll come over and attach our Go program to it, and I'll have it give us a status, and sure enough, we're in reset. And I'm going to go ahead and launch the program running, and you'll notice that down in the lower left, that's the counter that we saw in the code. So I'll hit K so that we run the 48 Hertz clock, and there it goes. It went through the boot sequence. That's why it stalled from 0 to 1, is just running through the boot. So now the program is running at 48 Hertz. I'll come back over here, and I'm going to artificially, well, in reality, I'm going to generate a real interrupt. And by doing that, I'm going to take the pin low, which is a falling edge, and that's how our code was set up, and bring it back high. And you can see that that triggered an interrupt, and for a brief moment the blue LED lit up. And I'll do that again, only I'll do it slower. I'll just hit L, and so it's back low, and now it's high. And it briefly flickers because remember through that code we were talking about, it's actually setting and then unsetting. So now with it high, I'll hit the T key, and that'll just keep clocking it. And you'll see that see the 2 green LEDs? They went high. One blinks much faster than the other, but for every green LED that blinks, we get an extra count, and there it goes. It recycled on 8, and I'll do it. And now I'll just keep pushing the button real fast, and you'll know that it doesn't keep counting as I'm pushing the button. And that's because the interrupt handler is constantly running where there's no chance to update the output display until you've stopped generating the interrupts. And there you go, the interrupt circuit is working as expected, in this case at 48 megahertz. Now let's give the 18 megahertz version a try. So we'll go ahead and compile that, and now we'll need to bake it in. So I'll come over here to the make terminal and type make, and while that's going to town there, we'll take a look at the source code. So over here to the right is the top, and I want to show you that that light, that blue LED that was blinking intermittently, is the triggered flag. And remember, in our code in the control matrix, when we receive an interrupt, we set that flag to a 1, and eventually it's cleared out by setting the reset, and that happens in 2 states, so it'll stay on just long enough to be visible. That's why we see the blue light only momentarily. We don't see it on or off, we see it flicker. That's doing exactly what it's supposed to do. Now in the 18 megahertz, when we run that, you won't see it flicker at all, and neither will you see the green LEDs flicker. So let's head back over to the terminal and take a look at what we have going there. So bring the terminal back up, and it's still compiling, and as soon as it's uploaded, we'll reattach. There it goes, it's went back up. So we'll bring our display here up out of the way, or up higher so we can see it. We'll come over to our terminal here to the UART, and we'll make sure that the pin is high. There it is, I hit the H key. And we'll come back over here and we'll hit S again to reset. There it is. Now this time I'm going to hit the L key, the L command, and that's going to run it at 18 megahertz. And there it goes. You can see that it's, even with that delay of 4 Fs in there, it's still counting pretty fast. But I chose that so we could see it count through the numbers relatively quick. So at this point, the processor is now officially running at 18 megahertz, and it's showing us the counting. So I'll come back over here to the terminal, and I'm going to toggle the interrupt flag. There it goes, and it counted. Now you notice that the blue, you couldn't even see the blue flicker, and I'm going to continue to do that. And the interrupt, you couldn't see the green. So I'll do it again. I'll hit the T key, and that'll trigger. And you can see that it's counting, but we don't see any green flickering. It's actually lighting, but it's lighting for only microseconds, and so is the blue LED. But you can see that we're counting right up, and I can hold my hand on the interrupt and it'll just sit there and count rapidly fast through the thing. So the code is actually working at 18 megahertz as well. Excellent. And I can sit here and just tap the T key, toggling through, and it'll just sit there and count. Now the reason why we can actually see the interrupt counter, the blades LEDs count, is because at 18 megahertz there is plenty enough time to get through some of the counting code of the 7 segment. That's how fast the 18 megahertz is that we're seeing. And you'll notice that on the 7 segment, when I hold my hand on it, the counting becomes a little jittery and off. But and if I take my hand off, it starts counting a little bit more stable. But again, we're only counting up to 3F. I set it so that we could test the clearing code. And that's it. There you go. We now have the RISC-V running at 18 megahertz with interrupts enabled. And finally, let's take a look at what the utilization was in the end, or the damage, as you will, if you want to think of it that way. We ended up using 3,500 LUTs, a vast majority of which, about more than 50%, was the test harness and everything with the UARTs, the parallel register, everything. That consumed the same amount of RAM as before, same I/O. We didn't add any I/O, and we're still using only 7 of the. We did actually go up 1 buffer. When I added the CSRs in, the tool just realized that it needed to use yet another global buffer in order to route clocks probably to that portion of the circuit. And if we look all the way down here at the bottom, we'll see the frequencies that ultimately we were able to achieve with the test harness in there. This frequency here will go up when we start removing the test harness. But right now I've set it at 18 megahertz and it's running just fine, as you can see up here to the upper right. It's counting along at 18 megahertz, including that large delay that we added to it. So excellent. Nice. Ranger RISC is now running at full speed, with interrupts too. This also means, unfortunately, we've reached the end of our RISC-V journey, which begs the question, where do we point our sails to next? Well, I have several projects that I'm interested in, all involving FPGAs, and here is a list in no particular order. We're looking at maybe doing some neuromorphic engineering work for neural networks with synapses and neurons, single board computers such as MacDyn's ICE board here that I picked up, and that looks pretty fun. It has all kinds of things all over it, some memory, the ICE chip, HDMI, you name it, a PMOD connector. Looking at doing GPUs, software like a basic monitor, maybe even a really basic OS. These are all just things I'm coming up with that I find interesting myself. And of course we have the BlackiceEdge right here. There's still a lot to do with this. It has a lot of things on it. It has HyperFlash, HyperRAM, the VGA connector. We're looking at maybe doing some more SPI with memory and TFTs and maybe the I/O expanders that I've messed around with, and perhaps even a platform level interrupt controller, which is something I'm very much interested in doing, especially if we use multiple SPI type devices. And perhaps a more robust assembler, because the assembler I put together is really just a hack job that was meant just for the series. But there are some things I'd like to do with it in terms of using Bob Nystrom's crafting interpreters book. On the next level, I'd like to mix it up a bit and play around with this ISIS computer right here and perhaps implement something like a ZX81 or simpler, not fully featured. I may be able to, if time permits, interleave some episodes involving neural networks and as soon as I can define a workable goal. In the meantime, I'll start preparing this HDL code, put it into two separate repositories, one with the debug in it, which has all of those exposed internal mechanisms in it. It's really bloated. It came out to a little over 4,000 LUTs when all is said and done. And then the release version, which is stripped down and just the RISC processor so that you can take a look at it. There is so much to do and so little time. So until next time, peace.